Welcome to the deep dive. This is where we take a whole stack of sources, um, really dig into them, pull out the key insights, and basically give you a shortcut to understanding some pretty complex topics.
That's the goal.
And today, we're heading into the very fabric of our built world. It's fascinating when you think about it. Imagine standing in front of some huge structure, maybe an ancient wonder, maybe a super modern skyscraper. What does it actually take to make that happen? From idea to reality.
It's a massive question, spans millennia, really. You've got the first idea, sure, but then the detailed design, choosing the right materials, that whole intricate dance of construction itself, every single bit matters.
Yeah, it's not just hammers and nails, is it?
Not at all. It's art, it's science, it's deep history, complex management, constant innovation. It's all wrapped up in every building we use.
So our mission today is to kind of pull back that curtain. We want to connect these threads that might seem separate, like classical design ideas from way back when, and the super high-tech digital tools shaping cities right now.
We're drawing on architectural history, construction methods, different project management philosophies, building information modeling, a real mix.
Exactly. And the goal is for you, the listener, to get a shortcut to grasping the complexity, the sheer ingenuity, and just the massive human effort behind the structures that define our world.
And we're definitely going to zoom in on a particularly critical and often, let's be honest, financially painful aspect.
The
The cost of time. We'll be getting into the weeds on schedule delays and the claims that follow, which can genuinely make or break a project.
That's a huge one. So maybe you're an urban explorer, maybe a budding engineer, a history lover, or maybe you just look at a building sometimes and think, how on earth did they do that? And hopefully this deep dive gives you some aha moments, a new appreciation for the buildings around you, and crucially, a better handle on those battles over deadlines and dollars. Okay, let's unpack this.
Let's do it.
All right, let's kick off right at the foundations, literally. Architectural foundations, historical context, those enduring principles of design. We have to start back in ancient Greece and Rome, don't we? Where so much was first laid down.
Absolutely. And it's kind of amazing how much we still reference figures like Vitruvius Polio.
Yeah.
His work, the 10 books on architecture, it's not just some dusty old text, it's foundational.
Right.
He wasn't just describing buildings, he was laying out a whole philosophy. The idea that good building has to align with the nature of things. And he gave us those famous principles: firmness, commodity, and delight.
Which we'd probably translate today as what? Structural integrity, usefulness, and, beauty.
Exactly. Structural soundness, does it work for its purpose, and does it look good? These aren't just ancient ideas, they're completely timeless. Still guides architecture today.
And he got incredibly specific. I mean, the detail is amazing. I was reading about his rules for column thickness. How columns at the corners, because they're seen against the open sky, can look thinner.
Yeah, that optical illusion.
So he said, make them thicker by a 50th of their own diameter, just to counteract that perception. That's remarkable, isn't it? Thinking about human perception in engineering terms thousands of years ago.
It really is. It shows it's not just about the physical reality, but the perceived reality, how the human eye actually experiences the space and the form. Modern architects still grapple with this, even with all our computers.
So it's a timeless lesson from Vitruvius, designed for how people see things.
Precisely. And he didn't stop there. He laid out really detailed proportions for things like ionic order bases and capitals. It was all about creating a harmonious visual language. That kind of meticulous approach set a standard.
So from those principles, our sources talk about the experience of Greek temples, this phrase, the crisp interplay between the peristyle columns, that outer row, and the inner cella walls, and the straightforward relationship of the entrance porch to the colonnade. Sounds quite poetic. What did that feel like?
It created this real clarity, a sense of spatial order, but also grandeur that wasn't overwhelming. It was inviting. Imagine walking towards one, the rhythm of the columns, the light filtering through.
Guiding you in.
Exactly, a carefully choreographed experience. And then you see later in the Hellenistic period, cities took these basic types and really elaborated on them. Things like fountains, well houses, not just utilitarian anymore, but turned into urban showpieces.
Integrated into the streetscape.
Yeah, making the everyday beautiful. And they even standardized the sequence in public baths. The cold, tepid, hot rooms, the frigidarium, tepidarium, caldarium. That sequence directly anticipates the huge Roman bath complexes. They basically created a template.
Speaking of Rome, The imperial forums, just the scale is mind-blowing. They literally smashed through parts of the old city wall, the Servian wall, to create these huge open spaces described as a spacious lung for the choking crowds. That image is powerful.
It really is. And these forums were the absolute heart of the city. Not just markets, not just government buildings. They were everything. Political debate, law courts, religious rights, just social gathering spots. Massive public arenas.
So bustling with activity.
Totally. Imagine walking through the giant basilicas, the detailed sculptures, the triumphal arches celebrating military victories. They showcased the triumphs of its armies and the genius of its artists. But it wasn't just propaganda. It was the center of daily life, too.
And for people visiting from all over the empire, Syria, Britain, Spain.
It was a statement. This projected the might, wealth, and culture of an empire. It was designed to impress, to awe, to communicate the power and sophistication of Rome. Pure architectural assertion on a grand scale.
Okay, let's jump forward quite a bit now into the medieval and Renaissance periods. Craftsmanship, patronage, innovation, they all take on new forms. One thing our sources highlight is this cathedral crusade, starting around the mid-12th century. Now, this wasn't just about building big churches, was it?
No, far from it. It was a really interesting redirection of societal energy. You know, the church had been pushing crusades to the Holy Land, pouring resources into that.
Right, huge military campaigns.
But as maybe enthusiasm cooled or the cost became too high, they found a new focus, offering indulgences, forgiveness for sins, not just for fighting abroad, but for contributing to building God's house at home.
Ah, so you could gain spiritual merit by helping build the local cathedral.
Exactly. And this channeled immense resources, both money and human effort, into these incredible structures all across Europe. Whole communities got involved, from the richest nobles to the poorest peasants, contributing labor, skills, whatever they could. A massive collective effort driven by faith and civic pride.
So that must have spurred huge developments in craftsmanship. The sources mentioned stonecutters, for instance. Their work, their monumental sculpture, started getting way more attention, becoming more valued than maybe frescoes or metalwork had been previously.
Absolutely. The sheer ambition of these projects demanded new levels of skill. Masons developed new vaulting techniques. Stained glass artists pushed boundaries with light and color.
Yeah.
And yes, stonecutters truly came into their own.
Turning stone into stories.
Pretty much. Intricate carvings, statues. Stone wasn't just structure anymore, it was narrative, decoration. The guilds that formed around these crafts became incredibly important centers for knowledge transfer, passing skills down generations. These cathedrals were like living encyclopedias of craft, often taking centuries to finish.
Amazing. Okay, let's transition into the Renaissance. Andrea Palladio, his 4 books of architecture, another seminal work. But what's really striking about him is this blend of, well, aesthetic genius and incredible practicality. He really understood patronage and economics.
That's a key insight. His villas, they weren't just beautiful objects. They were almost like smart business models for building, like Villa Emo. He often designed them to be built outward in symmetrical units from the spine, meaning a patron could start with the central core, the main house, and then add wings, loggias, maybe towers later on as they could afford it. It was almost modular, you know?
Yeah.
Scalable architecture, perfectly suited to the uncertain economy of the time.
That's fascinating. Designing for financial flexibility, basically pay-as-you-go building.
In a way, yes. Villa Emo is a great example, with the main house dominating the porticos and barns, all arranged symmetrically along that central spine. Or think about Villa Barbaro at Mazer, designed for some very important clients. It wasn't just beautiful with its ionic columns, but incredibly functional. It had the sophisticated water system, built-in fountain, fish pond, water pipe to the kitchen and gardens, blending classical beauty with really practical, advanced living systems.
He was thinking about the whole package. And his last work, the Teatro Olimpico in Vicenza. Even though there were apparently issues after he died, the sources mentioned the ceiling over the stage being irrelevant, and the connection between stage and seating left to chance. It's still seen as incredibly significant, preserving the Renaissance itself. How so?
It preserved the idea of the Renaissance, maybe more than being perfectly executed in every detail. It was this amazing recreation of a Roman-style indoor theater, a powerful statement of humanist ideals returning to classical forms.
Even with flaws, the concept was powerful.
Exactly. The dedication to classical forms in that specific context made it a symbol. People still went to see classic plays there, sitting in those classically bruising seats. It kept the Renaissance spirit alive through the architecture itself, a living monument.
It really highlights how architecture responds to its time economics, society, while striving for those timeless principles. Idealism meets pragmatism.
A constant balancing act.
Okay, let's leap forward again into the 20th century.
Mhm.
The whole landscape changes dramatically. We see movements like New Brutalism, mentioned in Rainer Banham's essays. Can you give us the quick definition of that?
Sure. New Brutalism, mid-20th century. It's characterized by, well, raw, concrete béton brut, leaving it unfinished, exposing the structure, often very blocky, monumental forms.
Bounds.
Well, the name stuck. But the philosophy behind it was about honesty of materials, functionalism. It aimed for a kind of social transparency. You saw it a lot in public buildings, universities, social housing. Controversial, sure, sometimes seen as cold, but it was a definite reaction, a move towards rethinking form and function, especially post-war.
And interestingly, even earlier, back in 1913, Walter Gropius, founder of the Bauhaus, was already talking about the unintentional beauty of American industrial architecture. Grain elevators, factories, comparing them to ancient Egyptian buildings. What was he seeing there?
He was seeing a beauty in pure function, I think, a departure from traditional European aesthetics, which often valued ornament. Gropius saw this raw power, this elegance in structures designed solely for their purpose.
Like the grain silos.
Exactly. The soaring forms, the repetitive elements of factories, the exposed machinery. He saw a monumental quality in their efficiency and scale, comparing it not to classical temples, but to the stark simplicity of ancient Egypt. It was a radical shift celebrating industrial honesty. What is beauty in an industrial age?
That new scale definitely translates into urban design, too.
Yeah.
Rockefeller Center, 1930s New York. Our sources call it the first major civic center, with buildings in a many-sided relationship. More than just tall buildings side by side, right?
Oh, absolutely. It was revolutionary. Not just isolated towers, but a whole complex designed to work together. High-rises, concentrating offices and shops, but also creating these amazing integrated public spaces like Rockefeller Plaza.
The gas rink.
Yeah, or gardens in summer. It wasn't just about building up. It was about creating a cohesive urban experience, managing crowds, creating a real place within the dense city, a totally new way of thinking about how buildings relate to each other and to public space.
But this era also produced figures like Robert Moses, hugely influential in shaping New York's infrastructure,
Yeah.
but also deeply controversial. The sources mention him bypassing commissions using roundabout means. Robert Carroll's work paints a picture of this dreamer planner doer getting accolades while maybe engaging in deceptions and innuendos. How do we square that circle? The achievement versus the methods.
It's the classic dilemma, isn't it? Ends versus means in city building. Moses had this image, this force of nature getting huge things done, bridges, parkways, parks. And he did get them done.
Unstoppable.
Seemingly. But Kara's research suggests it often involved tactics that weren't exactly transparent, like the Henry Hudson Bridge getting federal money for labor, city money for equipment, reducing the need for public bond sales, which would have meant more scrutiny.
Clever or maybe manipulative.
That's the debate. And when money for land acquisition for the parkway ran short, he apparently just rerouted it through Van Cortlandt Park, which was city land, avoiding condemnation costs and potentially lengthy legal fights.
So efficient, but at what cost? Parkland? Maybe public trust.
Exactly. It forces us to ask, what's the price of progress? Who benefits? Who pays? Displaced communities, environmental impacts, the erosion of democratic process. These are the tough questions his legacy raises. Our role here isn't to judge, but to lay out what the sources describe about this complex figure.
Okay, from grand designs to urban transformation. Underlying all of this is the stuff buildings are actually made of, which brings us nicely to part two. The material world. Craft, innovation, codes the substance of structures.
Yes, and material choice is never simple. It's always this balance, structural needs, looks, cost, and crucially, how it performs over time, how it weathers.
Like stone. The sources make a big point about variability. Some freestone weathers beautifully for centuries.
Right, looks great. But other types, they might look fine initially, but then disintegrate with the first hard frost or get eaten away by pollution pretty quickly.
It's that specific. You really need to know your local stone. There's an example of handheld stone from England. Apparently it grows tired with age after a few hundred years starts splitting.
Yeah, versus, say, Honester Pass slate, also from England, known for its lovely olive green and durability. But then nearby, Skiddaw slate, dark gray, is apparently less reliable, prone to splitting apart. It shows material selection is almost a hyper-local science. You need that deep, often generational knowledge.
And that detail extends to modern stuff, too. Concrete masonry units, CMUs, not just boring gray blocks, right? There are all sorts like channel bond beams, H blocks, A blocks. What's an H block for?
Okay, so an H block, viewed from above, it looks like an H. The shape makes it easy to lay horizontal reinforcing bars, rebar, within the wall as you build it up.
Ah, for strength.
Exactly. And a channel bond beam is sort of C-shaped. It creates a continuous horizontal channel within the wall where you can pour concrete and place rebar. It acts like a strong belt, tying the wall together, really important in earthquake zones, or for carrying heavy loads above openings. Smart ways to build in strength.
And insulating those block walls, you can pour in dry fill or use special systems like core fill, which have thinner connections, less webbing.
Right, to reduce thermal bridging, stopping heat from traveling straight through the solid parts of the block. It's all about improving that thermal performance, keeping heat in or out.
Wood, of course, is fundamental. But it has its own issues, doesn't it? It moves. The sources list all these types of warp: cup, bow, crook, twist, kink. Can you quickly explain cup versus bow?
Sure. Cup is when a board curves across its width, like a shallow U. Bow is a curve along the length of the board, end to end. Crook is a curve along the edge. Twist is when the ends rotate opposite ways. And kink is a sharp, localized bend.
And that's all down to how it shrinks unevenly as it dries.
Exactly. Wood is anisotropic. Its properties aren't the same in all directions, so builders have to anticipate and account for this movement.
And buyers need to know about board foot, that standard volume measure, 1 inch by 12 by 12. But also the difference between nominal size, like a 2x10, and the actual dress size after planing, which is smaller.
Yeah, that 2x10 is actually about 1.5 by 9.25 inches finished. Catches people out if they don't plan for the actual dimensions.
And then there are engineered woods, like wafer board, now usually called OSB, oriented strand board. Using wood efficiently.
Absolutely. Taking smaller strands or wafers of wood, often from less desirable species or parts of the tree, and bonding them together under heat and pressure with resins, creates strong, stable panels, great for sheathing walls and roofs, and it uses wood fiber very efficiently. Then you have light gauge steel framing.
Right, becoming much more common. Precise stuff. The sources mention minimum bearing for joists, 1.5 inches at the ends, 3 inches on interior supports. Why so specific?
It's all about proper load transfer. You need enough surface area resting on the support below to safely carry the weight without crushing the steel or the support, and things like strap bridging every 5 to 8 feet that stops the joists from twisting or buckling sideways under load, keeps them working together as a system.
And nested joists forming ridge beams, anchor clips, web stiffeners, lots of small details adding up to a strong structure.
Precisely. Each component plays a role in handling the forces involved. Then there are foam plastics for insulation, great R value, but fire safety is a big concern.
Yeah, maximum 4-inch thickness sometimes, strict limits on flame spread and smoke development, tested to specific standards like NFPA 285.
Critical safety measures. You want the insulation, but you absolutely have to manage the fire risk associated with plastics.
Okay, let's talk about putting the enclosure together. Walls, roofs, windows, doors, ICF walls, insulated concrete forms get a mention. What are those again?
They're basically hollow foam blocks, often interlocking like big Legos. You stack them up to form the shape of the walls, add reinforcing steel inside, and then fill the hollow cores with concrete.
So the foam stays in place.
Yes, the foam forms become permanent insulation on both the inside and outside of the concrete wall. Gives you structure and high insulation levels in one go. Very efficient. And when you put windows into, say, a stucco wall finish, you need careful detailing, flashing weep screeds to manage water and stop it getting trapped behind the stucco.
Right. Managing moisture is key everywhere. Roofs, too. Different insulation methods depending on the roof type.
Definitely. In a typical attic with a steep roof, you might have bat insulation laid over a vapor retarder on the ceiling, with space above for ventilation. For low slope or flat roofs, you often use rigid foam boards, sometimes in multiple layers, staggered to prevent heat leaking through the joints.
And things like purlin spacing those horizontal members supporting the roof deck, typically 2 to 6 feet apart, and how fasteners go through the top of corrugations on metal roofing, often needing special washers.
Yeah, all those details ensure structural support, proper drainage, and weather tightness. Keeps the water out and the roof on.
Steep roofs need proper underlayment, too, that layer underneath the shingles or tiles. Extra protection against wind-driven rain or ice dams.
Crucial second line of defense. And windows, they mention jam extensions. What are those for?
Adapting the window frame to different wall thicknesses. Basically, strips of wood or vinyl that attach to the inside edge of the window frame to make it flush with the interior wall surface, where the wall's total thickness. And weather stripping, of course, on the frame or the moving sash, vital for stopping drafts and saving energy.
Even a fireplace isn't simple. Factory-built ones need proper support, but the absolute key is following the manufacturer's instructions exactly, especially clearances to anything combustible and using the specific fire stops they supply where the chimney passes through floors or ceilings.
Non-negotiable safety.
Absolutely. Which brings us squarely to building codes and safety, the rules of the game.
Yes, often seen as red tape, but their purpose is fundamental: protecting public safety, health, and welfare.
They're the baseline. Adopted by local governments, they regulate design, construction, alteration, repair, everything, setting minimum standards based on how the building is used, its occupancy, and its construction type. Material standards, structural safety, fire safety, it's all in there.
And they're not static, are they? They evolve.
Constantly. Based on research, learning from disasters, unfortunately, and new technologies.
Right.
It's a cumulative body of knowledge on how to build safely.
And that occupancy classification seems key. Like whether it's residential group R, places people sleep, versus, say, a group B office building. That first decision dictates so much else.
It's fundamental. It influences how big the building can be, how tall, what materials you can use, how many exits you need, what fire protection systems are required. It really shapes the entire design from the get-go.
Fire resistance is obviously huge. The sources talk about firewalls. What makes a wall a firewall?
A firewall is a specific type of fire resistance rated wall. It has to extend continuously from the foundation right up to or through the roof. Its job is to completely separate parts of a building to restrict the spread of fire. And crucially, it has to be designed to stay standing even if the structure on one side collapses in a fire. Very high level of protection.
Designed for compartmentalization, basically.
Exactly, containing the fire.
Yeah.
You see other requirements stemming from occupancy too, like sprinkler systems often being mandatory in all Group R buildings, or special protection for trash and linen chutes in residential buildings because those vertical shafts are notorious fire spread paths if not properly protected.
Thinking through all the potential weak points.
That's the idea. Then there's means of egress, getting people out safely in an emergency.
Right, the escape routes. Egress width determines how many people the building can safely hold.
Precisely. The code calculates required exit widths based on the occupant load. The goal is a continuous, unobstructed, and protected path to the outside. And a key rule, if an escape path goes through a different occupancy type, its fire resistance rating can never be reduced. Safety is paramount.
No compromising the escape route.
Never. And things like horizontal exits moving between fire-safe compartments on the same floor. The refuge area you move into has to be big enough for everyone coming from the first area, plus anyone already there. They even specify a minimum area per person, like 3 square feet. It's detailed planning for worst-case scenarios.
And structurally, things like braced frames, moment frames, shear walls, these are specifically designed to resist horizontal forces, like wind or earthquakes.
Exactly. They provide the building's lateral stability, stopping it from racking or collapsing sideways under those loads, the unseen skeleton doing critical work, and finally, often overlooked but incredibly important, moisture management.
Ugh, the silent killer. Water vapor condensing inside walls or roofs.
Yeah, leading to rot, mold, or other deteriorating conditions. Big problems for the structure, big problems for occupant health. So, codes emphasize things like proper ventilation paths to let moist air escape, and correctly installed vapor barriers to stop moisture getting into cavities in the first place, keeping the building dry and healthy from the inside out.
Okay, we've covered the grand sweep of history, the nuts and bolts of materials and codes. But none of this happens without managing the whole process. Which brings us to part 3, managing complexity. Time, cost, project delivery, the art of orchestration.
And this is where we really get into the practical challenges, and often where the biggest headaches occur on projects, especially around time and money.
At the heart of it is the triple constraint theory in construction management: cost, time, and scope. And scope includes quality and quantity, right?
That's right. And the absolute key, as the sources stress, is that these 3 are closely linked. Change one, and you almost inevitably affect the others.
Increase the scope, add a feature, demand higher quality, and you're probably looking at more time and more cost.
It's a constant balancing act for the construction manager, trying to keep those 3 in equilibrium.
And time management. This seems to be where so many disputes flare up. The schedule isn't just a plan. It's a tool for monitoring, control, and evaluating time-related contract claims. This is where delays turn into potential legal battles, isn't it?
Absolutely. This is where time literally becomes money, and often big money. Understanding the schedule, and particularly the critical path, is paramount.
Okay, break down the critical path for us. Why is it so critical?
The critical path is the longest path through a network diagram schedule. It's the sequence of activities that determines the earliest possible completion date for the entire project. These activities have zero float or slack.
Meaning they have no wiggle room.
Exactly. Any delay to any activity on that critical path will directly delay the project's overall completion date unless you can somehow speed up something else later on that same path. It's the chain that dictates the project duration.
So float is the wiggle room on non-critical activities. The amount of time an activity can slip without affecting the final deadline.
Correct. It's buffer time, but
Yeah.
here's where it gets contentious. Who owns the float?
Ah, why is that a fight?
Because it's valuable. If a contractor finishes an activity early, creating float, can they use that time buffer later if they run into trouble elsewhere? Or does that float belong to the project, meaning the owner can use it up with a change order without granting a time extension?
So the contract has to specify who gets the benefit of that buffer time.
Good contracts do, yes. Because millions can ride on whether a delay consumed contractor float or project float. It determines who bears the financial consequences of delays.
Which brings us to the types of delays. The sources distinguish between excusable and inexcusable. What's the difference, and why does it matter so much financially?
Hugely important distinction. An excusable delay is caused by something beyond the contractor's control and not their fault. Think major unforeseen weather events, strikes, acts of God, things nobody could reasonably prevent.
Okay, so it's not the contractor's fault. Do they get paid for the extra time?
Generally, no. For a basic excusable delay, the contractor usually gets a time extension, more days to finish, but not typically extra money for their own extended overhead costs. That's often called a non-compensable delay.
Time, but no money.
Right, unless the excusable delay was caused by the owner. For example, the owner was late providing site access, or issued lots of design changes, or owner-supplied materials were delayed. That becomes an excusable and compensable delay.
Ah, so if it's beyond the contractor's control and it's the owner's fault.
Then the contractor typically gets both more time and financial compensation for the costs incurred due to the delay, things like extended site overheads, equipment rental, home office overhead allocation.
Okay, so that's excusable. What makes a delay inexcusable?
Inexcusable delays are squarely the contractor's fault. Poor planning, not enough workers, inefficient means and methods, correctable mistakes, self-inflicted problems.
So if the contractor messes up,
Basically, yes. For inexcusable delays, the contractor gets no extra time, no extra money, and might even have to pay the owner damages for being late, often in the form of liquidated damages. So, determining fault excusable versus inexcusable, and then compensable versus non-compensable is absolutely central to resolving delay claims.
this sounds like where good planning comes in. The sources mentioned the last planner system as a lean construction approach to tackle chronically low workflow reliability. How does that help prevent these delays?
It's about proactive production management. It started by focusing on weekly work plans, making sure tasks were really ready, well-defined, sound, sequenced, and sized. Basically, making sure the work can actually be done as planned that week.
Removing roadblocks before they happen.
Exactly. Then they added look-ahead planning, looking maybe 3 to 6 weeks out, to identify potential constraints, materials not ordered, drawings unclear, prerequisite work not done, and assigning someone to remove those constraints before they impact the weekly plan. It's about making promises reliable.
And they measure success.
Yeah, with metrics like percent plan complete, PPC. What percentage of the planned weekly tasks actually got done? Teams that consistently manage their look-ahead planning and reliably remove constraints tend to have much higher PPC, better cost performance, and fewer delays in claims. It's about creating predictable workflow.
That ties into a broader point from systems thinking, right? Delays in any system affect how fast it can react, how accurately it hits targets.
Absolutely. Delays introduce instability. The sources use the example of the electricity industry. The long lead time to build power plants means that forecasts made years earlier can lead to cycles of overcapacity or shortage because the system can't react quickly to changing demand. It causes oscillations.
And construction.
Same idea. Delays in information flow, material delivery, approvals. They cause ripple effects, inefficiency, resource conflicts, stop-start work, all driving up costs and increasing the likelihood of project failure or major claims. Timeliness is crucial.
Okay. Shifting focus slightly to cost management. The goal of an estimate is accuracy and completeness, aiming for the estimated cost to be greater than or equal to the actual cost. You want to build in some contingency.
You definitely want to avoid underestimating. Accuracy relies on nailing three things: quantities, how many units of work or materials; pricing, how much each unit costs; and productivity, how long it takes to do each unit of work. Getting those right sets the baseline budget and the targets for managing the project.
And estimates aren't a one-time thing. CMs do them at multiple stages: conceptual, schematic, design, development, etc. Why keep refining?
Because the level of information increases dramatically as the design progresses. A conceptual estimate might just be based on dollars per square foot for a similar building type. By the time you get to final design documents, you have detailed drawings and specifications, allowing for much more precise quantity takeoffs and specific material and labor pricing.
So the accuracy improves with each stage.
Ideally, yes, and it's crucial to use current market pricing for materials and labor, and to factor in cost escalation potential price increases over the project duration as a separate item. It's continuous cost verification.
And when costs do deviate from the plan, a variance analyzing why is key. The example of the insulation cost overrun is great. It wasn't higher material prices, but a 20% error in calculating the quantity needed.
Exactly. That detailed analysis tells you where the problem lies. Was it bad estimating, inefficient labor, unexpected site conditions, price hikes? Knowing the root cause lets you take targeted corrective action, and it's crucial evidence if that variance leads to a claim.
Yeah.
You need to know why the cost changed.
Which brings us right back to the sharp end. Change orders and claims. What's the difference again, and how do delays fit in?
A change order is a formal, agreed-upon amendment to the contract. It documents a change in the work and usually adjusts the contract price and/or time accordingly. Both parties sign off.
Okay, mutual agreement.
Right. A claim, on the other hand, is a formal demand by one party for something they believe they're entitled to under the contract, but which the other party disputes or hasn't agreed to via a change order. This could be for extra money, extra time, or both. Delays are a very common source of claims, especially when there's disagreement about who caused the delay and who should bear the cost.
So if a delay happens, and you believe it's excusable and compensable, but the owner disagrees, you file a claim.
Precisely, and that's where documentation becomes absolutely critical.
The detailed audit record trail, what does that involve? What do you absolutely need to prove a delay claim?
Everything. Meticulous record keeping is non-negotiable. Daily reports are vital, logging who was on site, what work was done, weather conditions, any delays encountered, visitors, deliveries, meeting minutes, especially from progress meetings, recording decisions, issues raised, responsibilities assigned, all correspondence emails, letters, tracking requests, instructions, changes, disagreements, photographs and videos documenting site conditions and progress. This comprehensive contemporaneous record is the evidence you need to reconstruct events and support or refute a claim. Without it, it's just opinions.
Contemporaneous is key, recorded at the time it happened.
Absolutely. Records created months later carry far less weight. And when quantifying the cost impacts of delays or changes, there are different methods. The sources mention the measured mile approach. Yes, that's often used for lost productivity claims. You find a period on the project where the work in question was proceeding efficiently, unaffected by the disruption. That's your measured mile. You calculate the productivity rate during that period. Then you compare it to the productivity rate during the period impacted by the delay or disruption. The difference represents the loss of efficiency, which you can then apply to the impacted work hours to calculate the cost.
Comparing efficient work to inefficient work on the same project.
Ideally, yes. If that's not possible, you might have to develop a reasonable estimate of what the cost should have been without the disruption, or conduct a detailed audit of the contractor's actual cost records for the impacted work. The goal is a fair and justifiable calculation of the damages. Overhead and profit percentages on change orders are often predefined in the contract, too.
And what about liquidated damages, those fees for finishing late?
Liquidated damages are amounts agreed upon in the contract before the project starts. They represent a pre-estimate of the owner's likely losses if the project is completed late. The contractor agrees to pay this fixed amount for each day they finish beyond the contractual completion date.
So it avoids arguments later about the owner's actual damages.
That's the idea. It provides certainty and incentivizes timely completion. But the key is that the amount must be a reasonable forecast of potential damages at the time the contract is signed, not a penalty designed purely to punish the contractor. If a court deems them excessive and punitive, they might not be enforced.
Got it. Finally, in this section, constructability reviews. Doing these during the design phase is much better.
Far better. This is a major reason owners choose delivery methods like Construction Manager at Risk, CMAR, or Design Build. You get construction experts, people who know how things are actually built in the field, looking over the designer's shoulder as the design develops.
What are they looking for?
Potential problems, things that will be difficult, unsafe, unnecessarily expensive, or just plain impossible to build as drawn. Maybe suggesting alternative details that are easier to construct, identifying sequencing issues, spotting potential clashes between trades early on.
Catching problems on paper, not on site.
Exactly. It's proactive problem solving. The goal is a smoother construction process, fewer changes, fewer delays, fewer cost overruns, and ultimately a better building that works as intended. Skipping thorough constructability reviews is often a recipe for exactly the kind of costly delays and claims we've been discussing. It's about prevention.
Okay, that's a fantastic overview of the complexities of management, especially the critical aspects of time and cost. Now, let's shift gears to the digital frontier. Part 4, the digital revolution in construction, BIM and beyond. Smart buildings, smart processes.
This really is a paradigm shift. Building information modeling, BIM, is fundamentally different from traditional 2D CAD drafting. It's described as a superior design environment. Instead of just lines on a screen, BIM uses intelligent parametric objects. A wall knows it's a wall, with properties like thickness, material, fire rating. A door knows it's a door and sits in a wall. If you change the wall, the door might adjust automatically or flag a problem. It captures design intent, not just geometry.
So it's more than a picture, it's a database. A digital database in which objects, spaces, and facility characteristics are defined and stored.
Precisely. And it's seen as part of a larger system for value delivery covering the entire life cycle, from planning portfolios of projects through design and construction, right into operations and maintenance of the finished building. A cradle-to-grave digital twin, potentially.
And it enables better analysis during design.
Hugely. You can run structural analyses directly from the model, simulate energy performance, analyze daylighting, test design options virtually before committing. This makes design, planning, and ultimately building much more efficient. And one of the killer apps is clash detection.
Right, finding where things literally collide in the virtual model.
Yeah.
Pipes hitting beams, ducts hitting lights.
Exactly. BIM software, or third-party tools, can automatically search for these geometric interferences by combining models from different disciplines: architectural, structural, MEP, mechanical, electrical, plumbing. You find these clashes digitally where they're cheap to fix instead of on-site, where they cause delays and costly rework. Huge time and money saver.
It prevents those oh no moments during construction.
That's the goal. And BIM goes beyond 3D. We're talking 4D and 5D BIM now.
Okay, 4D adds time.
Yes. 4D BIM links the 3D model elements directly to the project schedule activities, like that CPM schedule we discussed. It creates this graphically rich and animated representation of the planned construction sequence. You can literally watch a simulation of the building being built over time on screen.
Wow. What's the benefit of seeing that virtual construction?
It's incredibly powerful for planning complex phasing, coordinating trades, communicating the plan clearly to everyone involved. You can spot potential logistical bottlenecks or safety issues visually. It also lets you run what-if scenarios, try different construction sequences virtually to see which is most efficient.
And you can even include temporary works, like cranes or scaffolding.
Yes, good 4D models can include temporary equipment to check for site access issues, crane reach, safety clearances, really detailed constructability analysis based on the actual sequence of work.
Okay, so 4D is 3D plus time. What's 5D?
5D adds the cost dimension. Every element in the BIM model can be attributed to what it will actually represent in terms of resources and respective costs.
So clicking on a wall tells you not just its dimensions, but its estimated cost.
Potentially, yes. It allows for parametric and dynamic quantity takeoff. Change the size of the wall on the model, and the quantity of materials and the associated costs can update automatically. This promises more accurate estimates and frees up estimators' time from tedious manual takeoffs to focus more on analysis, risk assessment, and value engineering.
Sounds amazing. Any limitations?
Well, it's not quite push-button estimating yet. BIM models often provide only a subset of the info. Estimators need things like detailed labor rates, specific crew productivity, equipment costs often aren't automatically generated. And for truly accurate automated quantity takeoff, you need really good standardization of BIM components and their data attributes across the industry, which is still evolving.
So huge potential, but still needs development and standardization. And there are other challenges, like inefficient interoperability.
That's been a massive hurdle. Different software packages from different vendors don't always talk to each other smoothly. Exchanging complex parametric models isn't easy. That NIST study from 2002 found this poor interoperability added over $6 per square foot to new construction costs back then, $15.8 billion annually. It's getting better, but seamless data exchange is still a major goal.
So architects using one system, engineers another, contractors another. Getting the models to sync up perfectly is tough.
It requires careful management and often specialized expertise to translate models between platforms without losing data or introducing errors, especially when you need different representations, like simplifying an architectural model for structural analysis.
Despite that, BIM does help with subcontractor coordination,
Sure.
especially for complex trades.
Oh, definitely. For things like steel fabrication or complex ductwork, exchanging detailed models between the main contractor and the specialist fabricators allows for incredibly precise coordination before anything is made. Catches errors, saves time, reduces waste significantly compared to working off 2D drawings.
And this all links back to lean principles, reducing waste, improving efficiency.
Absolutely. BIM is a key enabler for lean construction. It helps reduce the duration of both design and construction, partly by enabling that better coordination and clash detection, collapsing the time needed. It supports the goal of efficiently producing highly customized buildings with minimal waste.
So looking even further ahead, the vision gets pretty radical. Buildings becoming intelligent agents, learning from occupants, living with a home, not just in it.
Yeah, that's the idea of spatial cybernetics. The building itself becomes an interface, a connective tissue between the realities of bits and atoms. Using sensors, data, and learning algorithms, the building could adapt lighting, temperature, even potentially layout based on how it's being used and the occupant's preferences.
Your home anticipating your needs, your office optimizing itself for collaboration.
That's the vision. And it's not just about massive, complex, smart buildings. There's also the grassroots movement of Fab Labs, fabrication laboratories.
What are those exactly?
They're community workshops, basically, equipped with digital fabrication tools, 3D printers, laser cutters, CNC machines. They give people unprecedented access to tools, allowing them to design and make almost anything they can imagine, from small objects to furniture to prototypes.
So democratizing design and making.
Kind of, yes. Empowering individuals and communities to create, innovate, and build locally. It's a different facet of the digital revolution impacting how we think about making things, including parts of our built environment.
It points to a future where buildings are much more dynamic, responsive, maybe even personalized.
Definitely. Whether it's top-down BIM integration or bottom-up Fab Lab creation, the built environment is becoming deeply intertwined with digital technology, potentially making buildings active participants in our lives, not just passive shelters.
Wow, okay. That was quite the journey we took. We really covered the whole spectrum, didn't we? From those ancient foundations, Vitruvius worrying about optical illusions on columns,
Right, and the Romans creating those spacious lungs in their forums.
all the way to BIM models dynamically linking cost and schedule, 4D simulations, and Fab Labs putting making tools in everyone's hands. It's incredible evolution.
We've seen how design principles endure, but also how materials, techniques, and especially management practices have constantly evolved in response to new challenges and technologies.
And that common thread seems to be this relentless drive for optimization, right? Optimizing space, materials, human effort, and, as we discussed a lot, time.
Absolutely. From Palladio's modular villas for uncertain finances to the critical path method trying to nail down the project duration to BIM trying to eliminate rework. It's all about building better, faster, more efficiently, more predictably.
And we definitely dove into the often painful realities of when things don't go according to plan, the delays, the claims, understanding excusable versus inexcusable delays.
Compensable versus non-compensable.
That whole fight over who owns the float and why meticulous contemporaneous documentation is just non-negotiable if you want to survive a dispute. Time really is the currency of construction.
It absolutely is. Managing that interplay of time, cost, and scope is the core challenge.
So as we wrap up, here's something to think about. Our buildings are getting smarter. They're starting to sense, learn, adapt. Maybe we really will be living with our homes soon. What new questions does that raise?
Ethical ones, certainly. Aesthetic ones, too.
Yeah, if AI can design and manage projects with incredible efficiency, optimizing everything, do we lose something? Do we lose the unexpected quirk, the charming mistake, the mark of the human hand that's always been part of architecture? What happens to intuition when an algorithm can calculate the optimal solution?
It's a fascinating question. Will total integration and efficiency make our environments more predictable, maybe even sterile? Or will it free up human creativity for different kinds of expression?
The future of building isn't just about faster computers or new materials. It seems it's also about defining the kind of relationship we want with the spaces we inhabit and the role we want human judgment and imperfection to play within them, something to definitely mull over.